We have already learned some aspects of chemical reactions. In my video named Spontaneity Gives Free Energy, we have studied the feasibility of a reaction. In my video Chemical Equilibrium, we have studied about to what extent a chemical reaction may proceed. In this tutorial, we are going to learn about chemical kinetics, which studies the speed of a chemical reaction. A detailed study of the factors which affect the speed or a rate of a chemical reaction will enable us to control those factors and allow us to carry out the reaction at suitable speeds. This video will cover part 1, where I'll try to give a picture of the reaction rate of a chemical reaction and the rate law. Rate of a chemical reaction. It is the rate of decrease of concentration of the reactants, or it is the rate of increase of concentration of the products. Now let's talk of the reaction C2H5Cl gives C2H4 plus HCl. Here the rate of disappearance of ethyl chloride is this. The rate of formation of ethylene and hydrochloric acid all are equal. Only we put a negative sign over here because in this case the concentration is decreasing. Now see this reaction. Here when 1 mole of H2 or 1 mole of I2 disappear, 2 moles of HI is formed. The rate of formation of HI is double, so the rate is given as following. Note that the stoichiometric coefficient is put in the denominator. So for general reaction, the rate is given like this. All the stoichiometric coefficients appear in the denominator. The rate expression shown here is the average rate of reaction. If we measure the average rate of reaction by measuring concentration of the reactant as time progresses, we calculate that the average rate is not constant. It falls as the reaction progresses, or in other words, we may say that the rate falls when concentration of the reactant falls. So it is more appropriate to measure the instantaneous rate. Instantaneous rate is the rate within very small time. From the knowledge of differential calculus, the instantaneous rate is this. The delta sign is replaced by derivative d. The instantaneous rate can be found at a particular instant by getting the slope of the curve at that instant. Similarly, concentration of product may be analyzed as time progresses, and we get a curve like this. Note that this curve has a negative slope while this one has a positive slope, which is quite understandable. The rate law. Now, one thing is for sure, that the rate is proportional to the concentration of the reactants. However, we cannot write the rate law expression just by looking at the chemical reaction. The rate law should be determined experimentally, because the value of x and y may or may not be equal to the stoichiometric coefficients a and b. This k is called the rate constant. How rate law is experimentally determined? We take this reaction. We measure the initial rate of formation of NO2 by varying the initial concentrations of NO and O2. The results found are as follows. When initial concentration of NO is doubled, the rate of formation of NO2 increases 4 times. When initial concentration of O2 is doubled, the rate of formation is also doubled. When initial concentration of both NO and O2 is doubled, the rate increases 8 times. So in the rate expression, the rate is found to be varying with the square of NO concentration and vary with the concentration of O2 raised to the first power. Now this may seem confusing. The question may arise, why do so much hard work when we can directly write the rate expression by taking the values from the stoichiometric coefficients of the chemical equation? The reason behind this is that the chemical equation does not necessarily represent how actually the reaction proceeds. Many chemical reactions take place in steps. They are also called complex reactions. And the reaction that take place in a single step is called elementary reaction. In other words, complex reaction takes place in steps, each step being elementary. For example, this reaction takes place in 2 steps. Now let's forget chemistry for a while and see this. This is the final result of men's 100-meter sprint event in the Beijing Olympics. See the result. The time required to complete the sprint event is not this time. The slowest athlete takes the longest time, and this is the time required to complete the event. Now come back to chemistry again. Here, this is the slowest step, and this will determine the time of the reaction and not this step. The slowest step involved 1 mole of N2O5. So The rate law expression contained concentration of N2O5 raised to the first power and not the second, as would have wrongly been done if the rate expression was determined watching the overall reaction. If we experimentally determine the rate expression and see that x and y is not matching with A and B, we can actually predict that the reaction is a complex reaction, where more than one step is involved. This is called reaction mechanism. Molecularity of a reaction. The number of molecules involved in an elementary reaction, not a complex reaction, is the molecularity of a reaction. Molecularity more than 3 is rare.